In Unit 9, we're going to be looking at systems of linear equations. And so we need to first understand what is a system of equations. A system of equations is basically two or more equations that share the same variables. So for example, if I give you this little word problem, the sum of two numbers is 6. Well, I don't know what those two numbers are, but I can make x my first number and y my second number and know that their sum is 6. And there's infinite solutions to this equation. It could be 1 and 5, 2 and 4, 3 and 3, but I could also do decimals or fractions, right? 1.5, 4.5. I could go into negatives and positives, -1 plus 7. So there's infinite solutions to this one equation in two variables. But if I give you a second equation, and I also tell you, given these same two variables, same two numbers, the second number is twice as large as the first number, I now have two equations with the same two variables, and I call this a system of equations. Now there are not infinite solutions to both equations, an xy pair that works in both. And so what we're going to learn this chapter is we're going to come up with 3 different ways to be able to solve this system of equations. This one, we could probably even use just guess and check and say, well, I know if x is 2, and y is 4, it would add to 6, and it would also balance this equation. So you could say, well, 2 comma 4, or my two numbers are 6, 2 and 4. But we're going to today focus on how can we find the solution to a system of equations graphically. So using our graphing skills to find that solution. So let's consider the system of equations 2x plus 3y equals -12 and 4x minus 3y equals -6. Now this one is not so intuitive. It's difficult to try to just look at it and go, oh, I know what the x and y that works in both equations is. So what we can do is we can take each equation and we could graph it. So if I graph the first equation, again, we have to put it into slope-intercept form. So I move the 2x to the other side. I divide everything by 3, and I get y equals -2/3 x minus 4. And so my y-intercept is -4, and my slope is -2/3. So down 2, right 3. I'm running out of space, so I'm going to go the other direction, up 2, left 3. Up 2, left 3, and then I can draw my line. And I don't have a ruler, so I'm doing the best I can. Put those key points right there. Now I'm going to take this equation and I'm going to do the same thing. So I'm going to move the 4x to the other side and leave the -3y on the left. Divide everything by -3. I get y equals 4/3x plus 2. So this time I'm plus 2 for my y-intercept, and 4/3. Rise 4, it's a positive slope, so I rise 4 and run 3. And I can see it's down here, so I could also go down 4, left 3, right? A negative makes a positive. And I can see that my graph intersects at one point, right? Because all of the points on my red line satisfy that equation. All of the points on my blue line satisfy that equation. So the one point that falls on both lines satisfies both equations. So the point of intersection, or in this case, -3, -2, is a solution to both equations, which is the solution to the system of equations. It's the one xy pair that works in both. Let's verify this solution. How can we verify this solution? Well, this xy pair has to balance both equations, meaning when I put -3 in for x and -2 in for y, it should work in both. It balances out. So let's try the first one. 2 times -3 plus 3 times -2 equals -12. -6 plus -6 equals -12. Yes, it works in the first equation. Now let's try the second equation. 4 times -3 plus, nope, that one's a minus. -3 times -2 equals -6. I get -12 plus 6 equals -6. And yes, it does. I can also, by looking at my graph, I know lines only intersect once. I know that is the only solution that works in both. There are no other xy pairs that balance this equation because two lines at most intersect once. So, a system of linear equations is two or more linear equations involving same variables. It can be represented graphically in order to make comparisons or solve problems. The point of intersection of two lines on a graph represents the solution to the system. It's an ordered pair or an xy pair that balances both equations, right? So if you're to graph two, so if you're comparing how much it costs per data, you can see that plan A here is less until you get to a point in which they cost exactly the same. Now plan A costs more, right? Or if I was, let's say I was emptying a pool of water. One pool has this much water and it's draining at a certain rate. And then we have another pool with so much water and it's draining at a less rate, smaller rate, decreasing at a smaller amount each time. You can see there's one point in time in which both pools have the exact same volume, okay? Or you can see at what time, the exact time in which pool A has a greater volume than pool B, and then at what time pool A has less volume than pool B. And so you can compare. Using graphing, you can not just find the point of intersection, but you can talk about what's happening before. So that's the nice part of graphing. You can visually see what's going on. If I was to give you tables of values, and I said, okay, well, here's 2 minus 2x, and here's x minus 7, so those are two different functions using the same x, y. So when I plug in 0 for the first, I get 2. I plug in 1, I get 0. I could plot that. I could plot in 0, 2, 1, 0, 2, negative 2, 3, negative 4. Etc. And I could go along and graph that. So something's happening. 2, negative 2, there we go. And I could graph it. And then I could graph the second one. When I plug in 0, I get negative 7. When I plug in 1, I get negative 6. When I plug in 2, I get negative 5. When I plug in 3, I get negative 4. There we go, and we can graph that, and you can see there's one point of intersection. I didn't really need to graph it though, because when I look at this, I can see when I plug in 3, I get the same output. 3, negative 4 is my solution. So just looking at your table of values, when you're getting the same x, or the same y for the same x, that is a shared point. Let's try one more, solving this system of equations graphically. I can graph this first one, y equals 4 minus x. Again, you can graph two different ways. You can make a table of values, plug in 0 for x, plot y, plug in 0 for y, plot x, connect those 2 points, or you can put it into slope-intercept form. It's your choice. So if I was to make a table of values for this one, when I plug in 0 for x, I get 4 for y. When I plug in 0 for y, I would get 4 for x. So I could just plot those. Or I could have rearranged this for, and then using my slope of negative 1, down 1, right 1, down 1, right 1, down, you get the same thing. But we get the idea. There's the first equation. The second equation, negative 2y equals negative x plus 10, divide everything by negative 2. Again, I could have, made a table of values as well. It doesn't matter. A negative divided by a negative is a positive, so I get 1/2 x minus 5. So negative 5 is my y-intercept, and my slope is 1 over 2. 1 over 2, 1 over 2. And there we go. So we've graphed both lines, and we can see the point of intersection is right here. This point of intersection is 1, 2, 3, 4, 5, 6, comma, negative 2. And again, we could go ahead and verify it by plugging it in both equations. And making sure that it works in both equations. If I just asked you to verify, for example, if I gave you 2, 5 and asked if it was a solution, you could go ahead and graph both of them and see if it's a solution, or you could just verify. But when you verify, you have to make sure it works in both equations. So you start off with the first one, plug in 2 for x, plug in 5 for y. I get 6 minus 5 is 2. It doesn't even work in the first equation, so I don't even test the second one because it has to work in both. So 2, 5 is not a solution to both. Whereas if I go over here and I plug it in, I say, okay, well, let's plug in negative 2 for x, 3 for y. I get negative 4 minus 15 is negative 19. Oh, it works in the first one. That's great. But it doesn't mean it's a solution to the system because it has to work in both. So now I go and test the second one out. So it has to work in this one as well. So 3 is y. Negative 2 is x. Does this work? I get 15 plus 6 is 4. That does not work, so this is a no. It is not a solution. It's on the first line, but it's not on the second line. And this one's not on the first one. I'm not even going to check the second one. It doesn't matter. So these are both no. Has to work in both. All right, so you can solve a system of equations by graphing. You graph each line. It's a linear system, so you know they're aligned because they're both degree 1. You can graph your line using table of values, or you can graph your line using y equals mx plus b. Once you've graphed your 2 lines, the point of intersection is the solution to your linear system. If I ask you to verify whether a point is a solution, you can just plug that point in to your x and y, and it has to work in both equations.